Welcome. On the agenda for today is the development of a simple, intuitive, classical description for the molecular polarizability and nonlinear polarizability. So we're going to come up with an intuitive one-dimensional description of how and why frequency doubling can arise and frequency mixing as well, and then extend that to 3D and then explore how these classical models actually play out in terms of quantum chemical calculations. So if we think about the linear polarizability as a prelude to the nonlinear polarizability, if we've got a transition, for example, if we look at this oscillation, this is what you're showing here is a time evolution of this is an isosurface for the time evolution of a linear combination of an S and a P orbital. So the S is even everywhere at time zero. The P has this sort of symmetry, and if you add them together in a linear combination, you're going to get something that has electron density that is transferred over to the top part of the molecule. And then over time, the signs invert because each of these wave functions evolves in its own time dependence based on the energy, and the energy difference results in an oscillation. An interference oscillation that results in constructive interference in this form at some later time, such that the electron density is then sloshing down, and this sloshability gives rise to this electric dipole in which light can couple with the matter to go from a ground state to an excited state, for example. So the sloshability in this case is related to real two states, the s orbital and the p orbital, but it's a simple description of how electrons slosh in response to an electric field, and that sloshing can drive, in resonance, it can drive absorption and emission, and off resonance, it can just sort of slosh around a little bit and generate scattering. So this linear polarizability is intimately connected to electron sloshability, if you want to think of it that way. So we can describe quantum mechanically the linear polarizability by the curvature of the potential energy, H, the internal energy, as a function of the electric field, E. So you can think of if we apply an electric field and we induce a particular internal energy, if we have a steep curvature, then we induce a greater internal energy for the same sloshing. For the same electric field, the same applied electric field. And so the curvature of this surface is intimately connected to the magnitude of the sloshability. A steeper curvature of the internal energy with respect to applied field corresponds to a larger sloshing. And so your linear polarizability is given by the second derivative in a one-dimensional system with respect to the electric field. So let's now consider what happens in the presence of an anharmonic potential, where the third derivative is non-negligible, and we have an asymmetry for the internal energy as a function of a field applied on the upstroke versus the downstroke. If we ask ourselves, if we were to roll something on this potential energy surface and ask what sort of induced dipole would we expect, we can imagine that as something is rolling along, it's going to see a steep potential energy on the downstroke, and so it'll turn around fairly quickly. But over here, the potential energy surface really flattens out, and so something can hang out there for quite a while before rolling back. And so that in the time domain, we're going to see a distortion in the induced polarization that will follow the black trace as opposed to the red trace. And that distortion is going to scale with the curvature, the asymmetry in the potential energy surface, the internal energy with respect to applied field. So how does that give rise to nonlinear optics? That's just simply a time-dependent polarization. Well, we can make that black trace in time by adding together the red trace and the blue trace, which is the doubled frequency. So if we add up the red and the blue, we end up flattening out the top and sharpening up, peaking up the bottom. There's also a DC offset we can throw in for optical rectification. And we can see that even though we're making the black trace in time, we can conceptually think of that as the linear combination of the red and the blue electric fields. Now, we can drive, if we're driving this, so the red we get from the linear polarizability. That's exactly the same thing we're driving it with, just maybe with a phase shift for the emission. But for the blue, we are now actually generating light at a very different wavelength, 100% difference in wavelength, the doubled frequency. And it turns out that's what we can detect quite easily in nonlinear optics, even though we may only be making a few photons of blue and driving it with a very large field in the red. Because they're separated by 100% in energy, it's very easy to even count those individual photons. So that's sort of a conceptual physical model for how we generate frequency doubled light from an anharmonic potential energy surface. This description, even though it's still a simple one-dimensional and to this point very qualitative, it actually provides a lot of good insights into the symmetry properties of nonlinear optics. So let's consider an assembly in one dimension where we have one molecule pointing up and another molecule pointing down. The red trace for each of these two components, oh, don't do that to me. Those are exactly the same. In other words, the linear polarizability doesn't care whether the molecule is pointed up or pointed down. It gives exactly the same response either way. However, if you look at the doubled frequency, these invert in sign in these two cases. Actually, I should switch over and use the blue. Okay, so the blue parts, we can see that the maximum in one is the minimum in the other, and vice versa. So for the blue parts, they're actually, if we add those two electric fields together coherently, they will cancel and result in zero contribution. So this sort of gives you a sense for the fact that order is much more important in nonlinear optics than it is in linear optics. So if we extend this idea to higher order effects, including third order nonlinear optical effects, for example, four-wave mixing or third harmonic generation, the key parameter there is the departure. If this is the harmonic potential energy surface, then the key aspect that results in higher order effects is the even departure from that parabolic surface. So there's a difference in the curvature as a function of this applied electric field that results in higher order contribution. So what we can do is sort of rank all of these in this one-dimensional system. The linear polarizability is just the second derivative of the internal energy with respect to applied field. The hyperpolarizability, it should be a minus sign here, is the third derivative, and gamma, describing four-wave mixing operations, is the fourth derivative. Now, if we want to extend this to 3 dimensions in 3-dimensional space instead of the simple 1D analog, then really the tensor elements that we generate are going to be derivatives with respect to applied field directions. Now, this is still the adiabatic polarizability, which is essentially just saying that all of the electron interactions are much faster than the electric fields used to perform the measurements. So this definitely applies in the limit of DC fields, but even in the limit of electric fields that are much lower in energy than any of the electronic resonances in the molecular system, the adiabatic polarizability is a reasonably good approximation. Okay, one of the big limitations of the adiabatic nonlinear polarizability, however, is the fact that it doesn't actually describe resonant phenomena. So if there's real resonances in the system where the excited states start to approach one of these two virtual states, for example, and it's shown here with respect to the doubled frequency, then the adiabatic polarizability can break down. That approximation can break down. And the reason conceptually we can think about this is that we make these virtual states through linear combinations of the real states, because these are not stationary states of the system themselves. They're transient states. So we build these time-dependent linear combinations, time-dependent virtual states through linear combinations, but the contributions of this particular state n to each of these two virtual states is now going to be very different if the energy gap between them is large relative to the energy gap between these two states. In other words, the closer this real state gets to one of these two states, the poorer the adiabatic approximation is going to be.